What if I said an ordinary steel rod that doesn't look like it's worth much turns into the ocean's most powerful guardian in just a few hours? Yup, that monster of an anchor chain, the one that keeps 1,000-ton cargo ships rock steady even in the middle of storms. But think about it. When 65 to 80-foot waves crash in the open ocean, why doesn't this chain snap? What kind of insane strength is built into it? Furnaces blazing over 1,800 degrees Fahrenheit, thousands of tons of pressure, and precision engineering down to the millimeter. Each link is forged like it's being prepped for battle. So come on, today we're diving into the mind-blowing journey from a plain steel bar to this beast of an anchor chain out on the high seas. It'll seriously blow your mind. Today, we're going inside the factory floors, the furnaces, the testing labs, and the minds of the engineers who build what might be the most underrated piece of safety equipment in the world. Stay with me, this is going to be way more exciting than you think. Every extraordinary thing in the world starts as something ordinary. An anchor chain? It starts as a rod of steel. But, and this is where things get interesting, not just any steel. Not the kind that makes your car door or your kitchen sink. Oh no, this steel has a story. The raw material for anchor chain is a specially formulated alloy steel, typically meeting international standards like IACs, the International Association of Classification Societies. These aren't just guidelines, they're the result of over a century of maritime disasters, hard lessons learned in the harshest environments on Earth, and a global commitment to making sure that what holds a ship in place never, ever fails. The steel must contain precise percentages of carbon, manganese, silicon, phosphorus, and sulfur, each element playing a specific role. Carbon gives it strength. Manganese adds toughness and resistance to wear. Silicon helps remove oxygen during smelting. The phosphorus and sulfur, they're the villains of the story. Too much of either, and your chain becomes brittle, prone to cracking under stress. Exactly what you don't want when a Category 4 hurricane is testing your anchor. The steel arrives at the chain manufacturing facility as long, round bars, typically 20 to 90 millimeters in diameter, depending on the grade and size of chain being produced. These bars are carefully inspected before a single thing happens to them. Chemical composition verified, dimensions checked, surface defects cataloged. Because in this industry, what you put in determines what comes out, and what comes out might one day be the only thing standing between a ship and disaster. Here's what most people don't realize. The grade of steel chosen for a specific chain isn't arbitrary. It's calculated based on the size of the vessel, the anchorage conditions, the water depth, and even the geographical region where the ship will operate. A ship anchoring off the coast of Norway in winter faces fundamentally different stresses than one sitting in the calmer waters of the Mediterranean. The chain is engineered for its specific destiny before a single link is even formed. And when that steel rod enters the factory floor, orange-tipped, heated to temperatures approaching 1,200 degrees Celsius, it's not just raw material anymore, it's potential. It's the beginning of something that will travel the world's oceans, outlast most of the things built in that same year, and perhaps, just perhaps, save lives in a storm we'll never hear about. That potential, it's about to be shaped. Here's where the magic, or more accurately, the extraordinary engineering begins. That heated steel rod feeds into a machine that looks like something out of a science fiction film, a coiling and cutting device that bends the glowing steel into the shape of a chain link in seconds, not minutes, seconds. The rod is cut to a precise length, calculated mathematically to ensure that once bent and welded, the link will have exactly the right internal diameter, exactly the right bearing surface, and exactly the right weight. Watching this process for the first time is genuinely jaw-dropping. The machine grabs the steel bar with jaws of hardened tool steel. in a single, fluid movement, almost graceful given the brute forces involved. The bar wraps around a mandrel and forms the classic oval shape of a chain link. The ends meet, they overlap slightly. The link is bent cold or warm depending on the grade specification. Fun fact, the machines doing this bending can exert forces exceeding 200 tons. To put that in perspective, that's roughly the weight of 30 African elephants, all focused on one small piece of steel. Let that sink in for a second. But bending is only half of the story of forming a link, because a bent link with overlapping unjoined ends is just a fancy piece of curved steel. It's not a chain, not yet. To become part of the chain, to earn its place in the line that will one day hold a vessel in a raging sea, it must be welded. And not just welded, flash butt welded. Flash butt welding is a process that sounds like it was named by someone who wanted to make welding sound exciting. And honestly, they succeeded. In this process, the two ends of the bent link are brought together under immense pressure, and an electrical current passes between them, generating temperatures so intense that the steel at the joint momentarily becomes molten. The two ends fuse, become one. The joint is, at this point, actually stronger than the surrounding material, a counterintuitive miracle of metallurgy. During this welding process, every single link is interlocked with the links before and after it. You can't weld a link in isolation. You have to pass it through the previous links first, which means the chain builds itself sequentially, link by link, each new link born already connected to its neighbors. There's something almost poetic about that, a chain that literally cannot exist without community. Each welded link is then trimmed. Any excess flash material from the welding process is removed by automated machinery, leaving a clean, smooth joint surface. Inspected again, measured again. The tolerances at this stage are millimeter perfect. A link that's even marginally oversized or undersized could affect how the chain interacts with the ship's windlass, the powered device that raises and lowers the anchor. And that's not a conversation anyone wants to have mid-storm. The link has been born, but birth is just the beginning. If the forming process is the body of the chain link, heat treatment is its soul. And this is the part of the process that most people never think about, and yet it might be the most critical step of all. After the links are formed and welded, the chain goes through a heat treatment process that fundamentally transforms the internal structure of the steel. We're not just heating it to soften it. We're using temperature as a tool, a precise, controlled tool to rearrange the very atoms of the steel and give it properties that the raw material simply doesn't have. The process begins with normalizing. The entire chain, sections of it at a time, is heated in a massive furnace to temperatures around 900 degrees Celsius. At this temperature, the steel's crystalline microstructure, the arrangement of its atoms, breaks down and resets. Think of it like rebooting a computer. Any inconsistencies introduced during the forming and welding process are ironed out. The steel becomes more uniform, more predictable, more trustworthy. Then comes quenching and tempering, the dynamic duo of heat treatment for high-grade anchor chain. Quenching involves rapidly cooling the normalized steel, typically by immersion in water or oil. This rapid cooling locks the steel into a hard, strong crystalline structure called martensite. The result is steel with dramatically increased hardness and tensile strength. But here's the catch. Martensite is also brittle, and brittle is the last thing you want in a chain that needs to absorb dynamic shock loads as a ship pitches in a storm. Enter tempering. The quenched steel is reheated, this time to a lower temperature, around 500 to 650 degrees Celsius, and held there. This controlled reheat reduces the brittleness while retaining most of the strength gained during quenching. The result is a steel with a carefully balanced combination of strength, toughness, and ductility, the ability to deform slightly under extreme load without fracturing catastrophically. The specific temperatures, the duration of each heat treatment stage, and the cooling rates are all precisely calibrated for each grade of chain, each diameter of link, and each specification requirement. This isn't guesswork. This is decades of metallurgical science and real-world testing compressed into a recipe that must be followed exactly every single time. After heat treatment, the chain is visually different. The surface may have a different color, but the real changes are invisible, locked inside the steel, in the arrangement of atoms you can only see under a microscope. Changes that mean the difference between a chain that holds and a chain that doesn't. And in the world of anchor chain, that difference is everything. Now we arrive at the moment of truth. Every chain that leaves this factory will be subjected to forces that most materials on Earth could never survive. Before it goes anywhere near an ocean, it has to prove itself here, in a controlled environment, with witnesses, with calibrated machines, and with classification society surveyors watching every step. Because here's the brutal reality: you cannot afford to find out a chain is defective once it's deployed. Once that anchor is down and a storm comes in, there is no troubleshooting, no calling the manufacturer, no second chances. The chain holds or it doesn't, and if it doesn't,
let's not go there. That's what the testing is for. The primary test is the proof load test. Every length of chain, every single one, must be subjected to a load equal to approximately 70 to 80% of its minimum breaking load, held for a minimum time period as specified by the relevant classification society. Under this load, the chain must show zero permanent deformation, zero cracking, and zero signs of distress. It either passes completely or it fails completely. There is no partial credit in anchor chain testing. The test is conducted on machines that look like industrial torture devices, which, in a sense, is exactly what they are. Hydraulic tensioning systems apply forces that can reach into the thousands of tons, slowly and steadily loading the chain until it reaches proof load, then holding it there. The chain creaks and groans under the stress. The links stretch microscopically, and then they hold. For every batch of chain produced, a sample must also undergo the breaking load test, pushed all the way until it actually fractures. This is destructive testing, and those sample lengths are sacrificed for data. Engineers measure where the break occurs, how the material fails, what the actual breaking force was compared to the specified minimum. This data goes back into process refinement, quality control records, and the traceability documentation that follows the chain for its entire operational life. And speaking of traceability, every meter of anchor chain is marked permanently with heat numbers, cast numbers, batch codes, and grade markings. If something were ever to go wrong with a chain at sea, which, thanks to all of this, is extraordinarily rare, investigators can trace that chain back to the specific steel heat it came from, the specific furnace it was treated in, the specific test machine that verified it. Accountability all the way down the line.
Additional testing includes Charpy impact testing, which measures how much energy a sample absorbs before fracturing, particularly at low temperatures, because a chain that performs well at 20 degrees Celsius must also perform in Arctic waters. Hardness testing, dimensional inspection of every link in every length, and ultrasonic testing for certain high-grade chains, which uses sound waves to detect internal defects invisible to the naked eye. Classification surveyors from organizations like Lloyd's Register, Bureau Veritas, DNV, or the American Bureau of Shipping witness this testing independently. Their stamps and certificates are what make this chain legal to use, required by maritime law, by insurance policies, by port authorities worldwide. Without those stamps, this chain doesn't go on a ship, full stop. It survived the factory. Now comes the ocean. There's one last transformation before a chain earns its place on a ship. After all the forming, The welding, the heat treatment, the testing, the chain needs to be protected from the very environment it's about to spend its life in, because the ocean, as beautiful as it is also deeply hostile to metal. Salt water is essentially a slow-motion corrosion machine, and a chain without protection would lose structural integrity long before its design life. Most anchor chains receive a hot dip galvanizing treatment. The chain is cleaned, fluxed, and immersed in a bath of molten zinc at around 450 degrees Celsius. The zinc bonds metallurgically with the steel surface, creating a coating that not only physically protects the steel from seawater contact, but also provides galvanic protection. The zinc preferentially corrodes in place of the steel, sacrificing itself to preserve the chain's structural integrity. It's a heroic little coating.
For higher-grade chains or specific applications, alternative coatings or cathodic protection systems may be specified. Some chains are painted, some are bare, particularly for mooring systems where the chain operates underwater permanently and galvanizing alone isn't sufficient. The chain is then connected together using joining shackles, specially designed, tested components that allow chains to be connected to each other, to anchors, and to ship systems. These shackles are themselves subject to the same proof testing and certification requirements as the chain. Every connection point is a potential failure point, and nothing is left uncertified. The completed chain, typically supplied in shots of 27.5 meters, which can be connected together to reach the total depth required, is coiled, marked for final time, and prepared for shipping. The paperwork accompanying it is, frankly, impressive. Mill certificates, heat treatment records, proof test certificates, dimensional inspection reports, classification society certificates. A paper trail that tells the complete story of every piece of steel in every link. It loads onto trucks, it travels to port, it arrives at a shipyard, and somewhere a rigger with decades of experience runs their eye along its length, checks the markings, signs the delivery note, and begins the process of installing it through the ship's hawse pipe and windlass, link by link, into the chain locker below. The chain's journey is complete. Its work is just beginning.
The next time you're on a ship, or even the next time you see one from shore, take a moment to think about what's holding it in place. Not an algorithm, not a satellite system, not some invisible technological miracle. A chain made by human hands, guided by centuries of engineering evolution, tested to its absolute limits, and trusted with something that has no replacement: human life. And remember, the ocean doesn't care how big your ship is, only how strong your engineering is. Every single link in that chain is built to survive the impossible: crushing force, violent storms, and relentless pressure. One mistake and everything fails. That's the level of engineering the world runs on, and most people never even notice it. If this blew your mind, hit follow right now, because we're just getting started. Drop an anchor in the comments if you respect real engineering. Next episode, even crazier. Stay curious, stay unstoppable.